think this works perfect. Thank you. Okay, so we have about an hour and a half, and the content here is one workshop for about 50 minutes, and then we'll have 3 Lighten talks from my co-hosts, Arno, Ahmad, Ayush Gupta, and Kevin Kwok. I hope we're going to be able to figure this one out, because otherwise it's going to be really awkward. You guys will all have to like sit next to me as I show you the screen. So what we'll talk about today is, you might have seen from Brian's presentation, you know, the last talk during the CLS, Gupship was talking about how our mental model has evolved over time as we've been working on different projects. And one of the big updates that happened about a year ago was making this concept of PCD a bit more usable using pods and GPC. So the tickets you have for DEF CON, the frogs you have for DEF CON, they're all pods. You can operate on pods via these cryptographic machineries called GPC. And this summer, we started kind of like getting a bit frustrated with pod and GPC, because it felt like they were powerful yet brittle and not expressive enough. So what we've been working through over the last 4 months is an upgrade to that system. And there's a lot of like interesting challenges that we have had to solve. So what I'll go through today is kind of talking about how that happened, and then we'll do a bunch of live coding. That always goes well. And then afterwards, we'll have Arno and Ahmad talk about the circuits that we had to write, the zero-knowledge circuits that we had to write to make this new Pod2 system work. Then Ayush Gupta will come and talk about ZK email, which is a way to import emails which actually are cryptographically signed in a way we can make use of them. And it fits very philosophically with the rest of the system. Finally, we'll have Kevin Kwok come and talk about how we built the CyberFrog, these little chips you might have used that are framed throughout the conference where you can get some rare frogs from. So today it's all about pods, pod 1, pod 2, things that are philosophically pods that we don't call pods yet. It's the pod singularity. So that's the agenda. And the workshop I will go through has 3 parts. The first one is I will reuse some of the slides from the talk I gave on Wednesday. If this is boring because you've seen it already, just boo me and we'll go faster. Also, because this is a small classroom, one affordance we have is feel free to stop me at any time. We're not actually going to do set time Q&A. If you have a question, just raise your hand. One of the AV people will bring you a mic, and we can go through the question. So I'll go through some of these slides, then I'll pull up my trusty PEX. PEX is a Lisp REPL that we built that you can use to make pods and modify them, etc. So we'll do some live codings. And if we have enough time, I want to show you how the greater than logical operation in pod is implemented across the whole code base to kind of see like what it entails to add more to this logic. Okay, so to motivate this a little bit, our thesis at Park is that programmable cryptography enables this thing we call the universal data adapter, almost like a Turing machine moment for data. So just like we've had electronic circuits for a long time, but it took like the correct mental model to squeeze the most out of them by think of them as like this like abstract machine you can program. Similarly, we've had data for a long time, but it seems like we still haven't found the right abstraction to make data more than dead bits that are hard to interpret outside of the context they were created in. And while we don't claim we have reached the Turing machine moment for data, this is what we aspire to. And Another goal here is to get more out of data. We are in a world where data gets more and more valuable, yet at the same time, data gets locked up more and more into these data prisons, where like people want to protect the data at the expense of getting less out of it. One idea I've been talking about with people at DEF CON is Google, at least Google search, is making use of all of public's data for multiple people. You know, like what they gave you is like bundling a database with a bunch of data about the world that you can query. Dropbox is about private data for yourself, right? So if we draw the 2x2 McKinsey matrix, is there all of private data for everybody? And of course, that seems a little bit silly at first, but I would like to have a system that I can ask, hey, how many espressos did people drink yesterday? And we for sure know that. Like we have like a pretty good approximation of this across all the SQLite databases in the world, but it's really hard to be able to ask that question because data has these like contradictory push and pull where you're trying to secure it, which like makes it such that you can make you can extract less value out of it. And at the same time, the way to extract more value out of data is to kind of like centralize them in one place, which brings a whole share of problem. So yeah, we want to take data out of their data prison. We want to enable more interoperability and usage of data. And in doing that, break down silos. And one more thing I'll say here is that we want to be able to enable a pragmatic route towards data ownership in a world where data keeps increasing in value. And that is very pernicious, because if data keeps increasing in value, yet holding your data means your data does not create any value at all, the incentive to hold your own data just keeps decreasing over time, you know? So we want to be able to like get out of that loop. So that's the system we've built over the last year, Pod and GPC. Pods are packets of data that are specially issued, so they need to be issued in specific ways. And then GPCs are cryptographic machines that can ingest pods and make claims about them using ZKPs. So claims like, hey, the entry killed age in this pod is over a certain number, or my frog is more beautiful than your frog, or that kind of stuff. These are the kind of claims you can make with GPC. And it's great because it's quite flexible, yet performant enough to run on mobile browsers, and it's about production ready. But, oh yeah, and all of you are using it, because your tickets and your frogs are all pods in GPC. So the TLDR, how the system works is an authority comes together, attests to some data via an EDDSA job signature. They get a pod. You put a bunch of pods together into a GPC, and you get a GPC claim, and you can show that to a verifier and convince them of something. So the way it looks like is you sign some data, you get some serialized key value data. Here we'll take the date of birth as a specific entry. We'll trace through this whole computation. Then you can construct a GPC config that says, hey, I'm looking for a pod called ID card with an entry called date of birth, and I want to make a claim that it's in this range. And on top of that, there's also an entry called card holder, which won't be revealed, and I want this to match a private key I will put inside this GPC. That makes it such that other people cannot use your pods. And then out of that, you get a bunch of stuff that you can plug back into a function to verify the claim, and you get a Boolean value out. That's basically how Pod 1 and GPC work. It's great because it enables this architecture there, which, I mean, is kind of general. It's pretty general. Most ID systems actually today use that kind of like architecture where there's an issuer that issues some data to a client, and the client will make claims to a verifier, and the verifier can verify these claims. Okay, so, and on top of that, it's extremely performant, and you don't need new zero-knowledge circuits. And as I said earlier, during the summer of 2024, we wanted more out of our systems. And the reason we want more out of a system, which I remind you is this, is that, well, the first limitation is this system needs specifically issued data. So you need to go and like get people to issue data in a specific way, which, I mean, if you think about it, it's not going to happen. Second is it's limited to one round of computation. And a lot of the time, use cases of data needs more than one round of transformation. You know, one round of transformation is useful, but it would be great if we could keep executing more programs on top of our data and maintain the cryptographic integrity. And also, it's limited to single-pair use cases. What I mean by that is, while the GPC can hide things from the pods that were put into it, the person executing the GPC actually has to know about all the pods that flow into this GPC. So if, I don't know, me and my friend are trying to figure out which frog is the most beautiful, I have to give the pod to my friend, or my friend has to give me their pod. So it starts becoming a little bit tricky when you have multiple people and high-stake data. The world today has lots of cryptographic data, yet it's very heterogeneous. So anything from blockchains to email to TLS to national ID systems, they're all like cryptographic data, yet formatted in very different ways with different signature systems, etc. The basic use cases often require more than 2 rounds of transformation, and potentially a whole world might open up if we can have data flow through different aggregators and different services, yet not lose their integrity. Like today, most of the time, all of the data falls into like a big silo and then gets processed and consumed out of that. It's very rare for like 2 silos to ping pong data between each other. That's not where the things goes usually. And the sad thing is there's a lot of works on domain-specific systems out there for processing all that kind of cryptographic data, yet zero interoperability between them. And what ends up usually happening is companies or open source groups build a specific import, as an example, for email data or for TLS data, and build an entire ecosystem on top for consuming that piece of data, as opposed to having these packets be able to flow through like with each other. So one way to think about the unlock of cryptography is that zero-knowledge proofs enable trustless refactoring and import. So you can import cryptographic data, refactor it, etc., without losing its integrity. And the unlock of more interactive technology like FHE, CoSNARK, MPCs, that you can combine data confidentially across many people. So where we want to get to is this kind of like verifiable and interoperable computational graph. We import cryptographic data, we compute over it. AV people, can you be a bit quieter? Excuse me? Hey, guys, quiet. It's a classroom. So you can import data, compute over it recursively, and then export it to a verifier. So we think this addresses the limitations of the earlier system if we can get there, because as I said earlier, there's a lot of cryptographic data in the world, yet it needs to be transformed to be usable. Most use cases require multiple people to compute together, most of the time recursively over many steps of transformation. Okay, so that's it. Now you know why you're here. We're trying to solve this problem. So in order to do that, we had to solve a couple of problems. The first one is the program composability problem. What I mean by that is that, let's say you have a group, like a bunch of friends, and all of these friends issue you a piece of cryptographic data. So it's like an array of packets. You put this array of packet in a function that counts how many best friends you have. Imagine that the friend packet has a value called isBest. You get 13 out of that. Then you want to operate on this further. As an example, a different person or a different company wants to operate on top of this result that you got. And they have a function called isGreatFriendGroups, which tests how many best friends you have. And if you have more than 3 or 3, you're considered to have a great friend group. It's a pretty basic example of data that flows through multiple programs. So abstractly, it would look like this. You have a bunch of pods that come in, they go through a program, you get another pod, you go through yet another program, and you get your final pod. So the tricky thing here is, in order to implement this, you need the second program to understand the first program, right? If I were to tell you like 42 is the output of my program, unless you know what program I executed, this data type does not mean anything to you at all. Like data type out of its context is basically kind of useless. You can add things like schemas, etc., but it becomes very brittle very quickly. It's really hard to compose programs on top of each other. So let's say these two programs are built by different people at different point in time. There's one solution to this, which is like every time a program consumes data from a different program, you hard code the fact that, hey, I know this other program behaves this way. I'm going to interpret the output in that specific way. If you want to do it just in time or like dynamically, you need to start going into systems that are pretty hard to work without human interventions. Things like static analysis, formal proofs, etc. And we know from the halting problem theorem that in the limit, it's really hard, it's basically uncomputable for a program to analyze another program, or at least for some kind of properties. So the approach we've taken there is to essentially throw away the CPU model and go towards logic. So what I mean by this is, instead of, as an example, executing opcode in a virtual RISC-V CPU or WASM CPU, we execute logical operations, logical deductions. So you would have something like a logic virtual machine, where you replace memory slots with logical statements. So instead of this piece of data is at this slot in memory, it's like there is a statement that says there exists an A such that A implies whatever. That kind of logical statements. You replace opcode with logical operations or deductions. So here's a deduction as an example. If A is smaller than B, you can deduce that A is not equal to B. Or if A is defined as 10 and B is defined as 10, you can deduce A equals B. Data becomes theorems. Programs become proofs, so mathematical proofs. And your system now looks like this, where you have some pieces of data that exist that have been attested to. You treat them as axioms. And then through logical proofs, you produce theorems that they themselves produce new theorems, etc. And the reason why this works in theory is that math is built to be interoperable. I can give you a theorem. If you believe that theorem has been proven, you can prove more things using my theorem or my lemma. It's very much different from the story with programs and computation in general. So now if we take back this example I gave, the way you would turn this into is, you have the blue theorem, which is Justin has 13 best friends, and you want to get to the green theorem, which is Justin is a great friend group. And so if you write this down in plain English, you would have something like, I have 12 best friends implies I have more than 3 best friends. So now you get to a system with two kinds of proof, formal proofs and zero-knowledge proofs. The zero-knowledge proofs are used to both show that the formal proofs were executed correctly, but also as a way to remove specific inputs to the formal proof. As an example, if I construct a formal proof that shows that my age is over 21, I may want to remove the axiom that says what my age is, while you can still audit the audit trail of this axiom in the first place. So this is all a little bit abstract. That's why we'll do coding after this, and we'll see it either break or succeed in front of our eyes. So the great thing with this is that you can kind of compute theorems on top of theorems on top of theorems, at least if we build the system correctly. And as an example, I will show you a little bit how a very early version of our system works. So this is the list of logical statements that can exist in a piece of data. This is the most basic one, which is the value of a key is a scalar or a vector of scalar. This is basically what you usually have when you have data, which is the value of age is 26, or the value of, I don't know, something else is this list of numbers. But then on top of that, we have other kind of logical statements. So as an example, we have an equal statement that says, well, this key equals that key. This seems a little bit silly, because if you see the two keys, well, you can derive the equals to each other. But what if one of the keys is not there anymore, right? And it's used in yet different statements. Here's a ternary statement, which says that the sum of these two keys equals the third key, right? So you have to think in terms of logic and not in terms of computation anymore. Here's a list of operations. So operations, remember, there are deductions that are applied to statements to compute new statements. So as an example, the equality from entry statement takes two value of statements, and then it checks the entries within the value of statements, and if the entries are indeed equal, it produces a new logical statement that says the two entries are equal. Easy, right? So from a cryptography perspective, what we had to do is, instead of writing a ZKVM that has circuits proving the state transition of a CPU architecture, like RISC-V or WASM or whatever, we built a virtual machine that has circuits proving the logical operation on statements is done correctly. It's a cryptographically verified theorem prover, if you want. So this all seems, again, like very abstract. Why did you guys go all the way there to show that your age is over 18 or something like that? Well, the reason is it's very neat because when you get this to work, you can wrap it up with a programming language that looks like what people expect, but under the hood operates on logical operations. So you can make the user experience of using this pretty decent. But at the same time, now you get pretty good composability at the program level, as opposed to having these programs that output data types that you then have to compute over without really knowing what the previous program did. Okay. I'll go through this a bit faster because this is not really the point of this workshop, but another challenge we wanted to solve is this challenge of imports. So we want to turn verifiable data into value of statements. And we're happy having some value of statements have special meanings. So as an example, if you were to import an email, we are okay having some keys that says underscore from, underscore to, underscore timestamp. And these are not entries that can be set by the content of the email. These are entries that come from metadata about the email. The great things with importing everything as value of statements is that all of our machinery that operates on entries can be used to operate on things like public keys, like who sent the email, etc. So as an example, if I want to compute with one of my frogs are pod ones. In some ways, they're foreign cryptographic data from the perspective of the pod2 system. They're on different curves, different signing algorithms, different markalization. And so what we have to do is we have to build what we call an introduction gadget for this pod1. So you would write a circuit that would verify that the signature of this pod is correct. It would store the signer into a value of statement with key underscore signer, and it would copy each pod entry into an equivalent value of entry. And then you can take two frogs, you can import them, and then you can put together a statement that says, Todd is more beautiful than a mustache frog. So if you go through all of this, this is the kind of stuff you can do. So we want to be able to import all kinds of stuff, whether it's data from the web, data from blockchains, data from virtual worlds, even mathematical proofs themselves. And in order to do that, well, we also have to make it not too hard to use this system. If we go back to the place where you need to be a cryptographer and an expert in logic in order to use this, we've regressed. So it's really important this thing is not extremely difficult to use. So this is what the assembly of our system look like. It's a bunch of operations. Don't ask me why we use strings. You can ask Ahmad. No, I'm joking. Ahmad has been trying to remove the strings from the system. And so what you have to do as a user of the system is you basically have to craft a sequence of logical opcodes to make new pods. And also when you get a pod out, you have to read the logical statements and make sure they actually claim what you want to verify. So this is pretty hard to work with. So what we did is we built this this little logic programming language to create pods and verify them. It's currently a Lisp because it's the only kind of programming language you can write in 2 weeks, but we could have other things in the future. And it's great because it has an interactive development loop, so it's easy to play with it. So instead of showing you an example of PEX, I'm just gonna like do it live. So pray for me. Cool. So actually, I have a note here of you can do this with me if you want, but no guarantee that this will work on your computer. So if it doesn't, don't complain. If you go on github.com/xeroxpark/parknet, and you have Cargo Nightly, specifically this version, take a picture of it. You can run cargo build in a PEX crate and cargo run -- release. The -- release is important, otherwise everything is going to take like 5 hours. And you can follow along. If it breaks, please don't tell me, but it doesn't work, because I won't be able to fix it on your computer. Instead, you just start watching. But for some of you, it will work. I know for a fact that on Linux, it's really hard to get it working. Ahmad has been trying to put together a PR because there's a dependency on OpenSSL. Don't ask me why we have a dependency on OpenSSL that doesn't work. But on Mac, it should work. And on Windows, same thing. I don't know. I mean, my friend here, Alex, got it working on Windows as well. So we can look later. OK. So I will put the mic back, because I need both of my hands to type super fast. All right. So I will go just like you in the PEX crate, and I will just run the system release. OK, so so what this does, so you might notice there is a little statement that says REPL synchronized with other peers. The fun thing with this Lisp is it's actually a multiplayer Lisp. So when you boot up a REPL, you're actually connected to all the people that use the REPL as well. So we can do operations on our pods, etc. We'll try to get it working here, but it's not that important. The second thing that takes a while is we recreate the parameters of our circuits and the verification key every time we boot it up, because we don't want to serialize them on disk yet, because we change them all the time. So I'm in the REPL. You can see I have a public key. I have a little username. My username is Pulsar Voyager. And so what I can do with this REPL is I can create pods. I can either create pods out of nothing. If you remember my slides, it's like importing a pod. But because we don't have any good importing system yet for existing cryptographic data, the way I'm going to import pods, I'm just going to self-sign them. But you could imagine that if you were to import a pod as well and you gave me your username, we would be able to compute on top of each other's pod. What I can do as well is I can create pods from previous pods, which is really the key of the system. So let's make a pod. So also this language and also the logic only support numbers and list of numbers. So there are many things I would like to show that don't use numbers and use different kind of things. So you will see some of my examples are a little bit contrived, but it's because we have to work with what we have. So can people show hands if they have read the Lisp syntax before or something similar? So I can see whether I have to spend a lot of time on this. OK. So one thing to know about Lisp is that it's a very simple kinds of programming language. It's really easy to parse. The way it works is every time you see brackets, you try to find the closing bracket for this, and you have to imagine in your head that the computer is going to turn this into the result of that computation. So as an example, if I do +1, 2, it uses the infix notation instead of, sorry, the prefix notation instead of the infix notation. This means the computation I'm executing is plus, and it's over 1 and 2. So this is going to turn into 3. See, I get scalar 3. And if I want to do different things with different orders, I can keep putting brackets. So as an example, if I do +3, 4, what's going to happen here is 3 and 4 are going to be summed first, and then it's going to be summed with 1. So we're going to get 8 out of that, right? So if you don't understand the syntax at any moment, tell me, and I'll explain you how it works. But it's not as scary as it seems. And the reason why we wrote a Lisp, once again, is because it's really easy to write a Lisp parser and lexer and interpreter, whereas it's really hard to write a parser, lexer, and interpreter for imperative languages. OK, so let's make some pod. The first pod I'm going to make is almost like an ID card for myself. So what's this ID card going to have? And remember, we can only use numbers. So first, I have some form of like national ID. It's kind of like my user ID in the system. I might have an age on it. I know that the proper way to do this would be date of birth, but we'll skip that. So I'm 26. And also, in my ID card, I have the zip code I live in. I've never used zip code this much in my life, by the way. Zip codes are great because they're also a number thing about you instead of most other things. OK, so I press enter here, and I get a pod. And you'll notice that we get a useful debugging window here that tells us the type of our pod, that is the cryptographic machinery you have to use to verify the pod, is Schnorr-16. So Schnorr is a signing algorithm. So this is a self-signed pod that I just made about myself. And inside we have a bunch of logical statements. All of these statements are value-of statements. So they just make a claim about an entry in the system, in this specific pod. So you'll see that it claims that my age is 26, my ID is the number I typed, and my zip code is 12001. And on top of that, we have another value of statement that has been added automatically that I did not set, and that in fact I cannot set because it starts with an underscore, which is the public key that signed this pod. It's the same here. So you'll notice that, as an example for this pod, the public key, which is an important value in order to anchor that piece of information to reality, is something we can operate on the same way we can operate on other kinds of data. Public keys are not special in this system. They're just data. Cool. OK, so let's make another pod. And this other pod is going to be a pay stub. So this pay stub, it's issued by someone else. Ideally, I would be able to change my private key in the REPL. I can't. And also, if I exit the REPL, it deletes all my pods. So we're in this very annoying system where the pay stub is going to be signed by the same authority, but could be signed by a different one. It doesn't have to be signed by the same public key. So I have a salary, let's say 120,000 units. This pay stub is linked to an ID of someone using any kind of ID system, and that's it. So now I have another pod, same deal. We have some value of statements. Same, there's a signer in it. OK. So now what I want to do, if we go back to this computational graph, let me bring it up here. I have two pods, let's say pod red and pod green, which are pods that have been issued by different people. One is my ID card. Maybe it was imported from whatever horrible format the government uses to make ID cards be cryptographically verified. And then the other one is a pay stub. And imagine that's been imported using the ZK email system that Ayush is going to tell us about later, where it parsed my pay stub email from, let's say, like Gusto or your payroll system. Now I have these two pods. I want to make a new pod out of it. And what this new pod is it just says, I want to do a join on all of my data, which says like the ID, my ID has this much annual salary with this zip code, right? Let's try to do that. So what I need to do is I need to take two pods and I need to put them into one pod, and also need to create some logical statements that kind of like makes everything fit together. And it will make more sense as I write it. So we're going to create a new pod. Actually, let's do like an even more interesting example, which is not only do I want to show that I have a specific salary, I actually don't want to reveal the amount of salary. I just want to show it's over a certain amount, right? So we'll do salary over amount. That's the name of our pod. So first here, what we'll do is we're going to query for pods within this pod. And the thing that's important to know about what I'm going to do is that the queries are provable. So the way I express my query using this query language gets turned into a bunch of stuff within the logic VM that shows I've done this query correctly, which is, but also that it imports a bunch of statements from previous pods, such that a verifier down the line can be like, oh, okay, they truly imported a real ID, not something that they're like little brother signed or something like that. So on top of that, we're going to use a new piece of syntax, which is define, because as I query a pod, I'm going to get bindings to values in the pod, and I want to reuse them, so I will bind them to variables. Because you might have noticed in Lisp, there are no real variables by default. You just compute. So here, we'll need some variable-like stuff, otherwise it's going to get really gnarly. So first, we're going to query for things in my ID card pod. So we'll say, OK, so ID card ID, age, zip code. These are the names of the variables I want to bind the outcome of my pod query to. And we'll use this statement called pod question mark. And so what follows pod question mark is it's a query language. So what we'll do here with the query language is we're going to be very open. We're just going to say, hey, I want a pod that has an ID, that has an age, that has a zip code, and whose signer is equal to a specific value. OK? So what I'm doing here is what this query does is it asks for a pod with these three things, and also it adds a constraint for the signer. This constraint, currently, it's a plain text constraint. So what this means is it's not actually verified. I'll have to do something with the signer later such that like this query cannot actually be cheated later. So we'll get a binder to this as well. ID signer. Let's do it this way. OK. One thing you might notice is I cannot explicitly pass pods into autopods. I can only query for pods. The reason we've made this decision to only allowing for pods to be queried is because if you query for a pod, the query should include everything that's necessary for this pod to be then like used as a legitimate entry. So if a query were to return multiple pods, they should be equivalent. Because if they're not equivalent from the perspective of the verifier, then that means your query is not like tight enough. This is an aspirational goal. Maybe we'll have to change that. But for now, this is how it works. So we'll do another defined where we're going to get bindings to our pay stubs. So we'll have salary, and then pay stub ID. Same deal here. Salary ID. And then I'll also need. Also, if anything doesn't make sense, feel free to interrupt me and ask me questions because it's only gonna get crazier from here. Cool. Okay, so now I have all of these little variables, right? If the query succeeds, that is. What am I going to do with these things? Well, the first thing is I want things to be revealed in this pod, right? As an example, what I revealed is I revealed my zip code. So I'll say zip code. Remember, the syntax is key value, key value, key value. So I say there will be a key called zip code, and the value will be zip code, which I got from this pod I'm querying here. And then that's the only thing I'm going to reveal in the clear. Everything else I'm going to reveal are specific constraints that are applied between these pods. So the first thing I'm going to constrain is I'm going to say ID card ID equals pay stub ID, right? Because otherwise that means I'm using either someone else's pay stub or someone else's ID card. Then I'm going to make a claim that my salary is over 100,000 units. Another thing I'll do is I'm going to claim that the ID. So okay, what I want to do here is I want to show that the pods I've been using are from a specific signer, not from like my little brother or something. So there are two ways for me to do this. One way is I reveal both signers. Another way to do this is I reveal one signer and I show that it's equal to the other signer, which is equivalent, right? So we'll do the second way because it's more fun. So we'll say ID signer equals pay stub signer, and on top of that we will reveal the signer, which is ID signer. Okay, so are we using everything we got here? So we're using ID card ID. Oh, and age. What should we do with age? Over 18? Okay, let's do that. So I'm going to remove this closing thing, otherwise it's going to just create the pod. So age is over 18. Cool. Okay, so now we'll press enter, and if the demo god is on my side, this will succeed. Oh, it's working. All right, so we just made a zero-knowledge proof, and we created a new pod. What's inside our new pod? Well, we have a bunch of logical statements. Let's read this together because there's a lot going on. So the first thing you'll notice is that some entries now are prefixed, or entries used to not be prefixed. Entries that are prefixed are entries that provably come from other pods. The origin doesn't really matter, like what's written behind the column doesn't really matter. The only thing that matters is if it's written in two places, you know that this entry, both of these entries came from the same pod. The reason why it's really important to have traces of where entries come from is because you cannot, the point of a pod, the reason why a pod is a list of key value and not just a single key and a single value is because there exist in the world values that go together. As an example, I can't take my age and combine it with your name and make a new person out of that. These entries need to remain logically grouped. So that's why we have this. So let's read it together. Maybe we'll do the easy stuff first. So first we introduced a constant. Constants don't exist in the system. So we just said 100,000 equals 100,000. Or at least the entry named 100,000 as a string equals 100,000. We've this entry called zip code 12001, and notice that if you were just to see this, that doesn't mean that my zip code is that zip code. That just means that there's an entry called zip code in the current pod that has a specific value. There's another constant which says 18 is 18, and finally there's another entry in the current pod that says signer equals this public key. So if you were to just see these four blue values, that wouldn't really prove anything. That just says I just made a pod with a bunch of entries in them. What matters now is the relationship between these entries and previous entries through logical statements. So let's read them from the top. So the top says there's a pod whose origin ends with 973, and in that pod there was an entry called age, and it's over 18. There are two pods, one that ends with 973, the other one that ends with 226, where both of their underskiners were the same. The pod that ends with 226 had a salary entry, which is over 100,000, and both pods have the same ID. Finally, the zip code entry in the current pod is the same as the zip code entry in the 73 pod, and the signer in the current pod is the same as the underscore signer in the 73 pod. So this basically, as a claim, kind of like shows logically what we've been trying to show so far. Okay, so I'll stop here because we just did a lot. If there are questions, we can go through this like many times, so let me know if there are questions here so far. Yes, can one volunteer bring a mic? Oh, thanks, Arturo.
Thank you. Thanks for the introduction. If we assume that this is the technical capability, what would be an application?
So the current technical capabilities which have to do with importing data are pretty limited because we're just signing pods ourselves, right? So what this means is this is only useful currently if just like the pod 1 systems, people that are issuing useful data, like the SWAMP that issues your frogs, issues your frog as these Schnorr 16 pods, right? So if you could do that, then the way to think about the system is it's a way to operate on data and then make further and further refinement of data and combination of data in such a way that the data's integrity is maintained. So there's a couple of things you can do. One is I'll take the national ID kind of lens, even if it's not my favorite one, because it speaks the most to people, which is that if you expect a data issuer to be able to answer any kind of question that someone would want to ask about that data, it's really annoying for them because they have to do a lot of work. Ideally, what you want them is to want them to issue some data and be like, now it's your problem to operate on that data, but at least you cannot make like false data pretending to be me. So as an example, so I come from Belgium. If the government of Belgium, they're Europeans, so they're further thinking, they start issuing passports or national ID card using this Schnorr 16 pod. Now I can do things like go somewhere and prove my age is a specific amount, or I can claim a government benefit anonymously without being able to claim it multiple times, or I can use that to sign digital documents, or I can kind of like anything that involves my identity is just logical statements applied to my identity. As an example, signing a document is a pod that says the hash of that document as an entry, and then there is my, I don't know, ID number or something else there, provably coming from an ID card signed by the Belgian government. And
the required infrastructure would be that the government and your employer both have public keys?
Yes, so they do. The government has public keys. Your passport is signed. Your ID card is signed. So what I'm saying is the current system really sucks, right? Because you need people to issue their own pods. What we're trying to get to, and I thought we would get to there for this demo, but we did not. It's going to take us one more week, is the first demo of an introduction gadget where you can take existing cryptographic data that is in a totally different format and import it as a pod. And then you can operate on it. So what we were trying to do, but we didn't get enough sleep this week, is to import frogs, which are not Schnorr 16 pods. They're different kinds of cryptographic data, and then do operations on our frogs, right? So as an example, the NFC card in your passport is signed by the public key of your government, but it's using some garbage signature scheme. It's like a totally different system. So there are people today that build bespoke systems to operate on passports. What I would like to do is be able to import a passport as a pod 2 and then everything else that consumes pod 2. And does operation on pod 2 can use it. So on the verification side, you do need the person or the company or the program that is verifying this data to accept the truth of that data. So in some ways, you don't need infrastructure at the attestation side because we'll just be able to import it, but you do need infrastructure at the verification side. So I think the way we should start with this system is we should bring it to companies, not governments, that need to like essentially compute stuff on top of official data. And instead of them having to pay like $3 per verification for something like Persona, where they have to like get the video of you and your passport being watched by someone, they can just accept the pod 2, right? So of course they would have to make sure that all this stuff is audited, works correctly, but I think the way to bring this to market, sorry, we're going way out of bound of this workshop now, is to go to people that need data from other sources that needs to be processed in a way where it's cheaper for them to do so.
And last question, building on that. the verifier, what do they need?
The verifier?
Yes.
They just need a little program. And then what they get...
And they need the public keys?
They need anything that's part of the axiomatic pod to tie them to reality. So it might be public keys, it might be certificates authority. It will depend on each use case.
And the resulting pod, but not the input pods?
No, they don't need the input pods, they don't need the computational graphs. Yeah.
Thank you.
Thank you for your questions. There's a question in the front, Arturo.
Thanks. So this language is kind of like a relational algebra, the way that it's...
Yes, it's like
coded.
Prolog.
Yeah, and so when we're saying that we have... The programs now are provable in the sense that if you listed the queries and maybe the lines of evaluation, you could use some rules of inference to say that this computation is done by rules of inference and not by evaluation. And then when we talk about the zero knowledge proof, you're going to write a verifier of that algebra and snark the verifier of this algebra.
Yeah.
I just wanted to make sure I understand the two steps of because there's two proofs going on.
Yes,
One
there are two
is
proofs.
Yeah. It's kind of like this pi squared project that I heard about earlier this week a little bit.
Yeah, they use the K framework.
Yeah, but in a similar way, like they have this front language that's provable in some other sense of the word. Correct. And then I have a question. So Lisp is cool because it's also like homoiconic. So Lisp is data, code is data, and we're just giving examples that's pretty similar to the normal data that we're used to looking at. Is there a way that you can leverage this fact that code is also data in this framework, or that's, I mean, probably far out future, but
yeah, so this is a great question, and you will need to do this when you start doing first and second order logic, because you know this logic that we have right now is a bastard propositional logic. It has numbers. Usually propositional logic doesn't have numbers. It just has statements about stuff like it is raining or it is not raining. Here we have numbers. If you don't have numbers for the ultra nerds here, you would have to do it in a way where you define the 0 number and then you define successor. And so 3 is successor of successor of successor of 0, but then you see how gnarly it gets very quickly. So we added numbers to propositional logic. If you want to do first order logic, you're going to need to be able to manipulate statements via other statements, like groups of statements via other statements. And so the semantic of Lisp will help here quite a bit. Like I could imagine how this will be useful, but that's where we stopped.
Yeah, so the Lisp is, I mean, you said it's just a convenience for defining a language, but actually you might keep it because it's useful.
Yeah, it's possible, yes. The reason why I say that is because people get spooked out by the Lisp. Yeah. Like, oh, this is amazing, but I will never use it because it's a Lisp. You know, if there was a space elevator that required you to write some Lisp to go on, a bunch of people would not. Yeah. They were like, it's just too hard.
That's a good way of putting it. Thanks.
Cool. If anyone keeps more questions, let's go.
Thanks for the introduction. More on the verification side. The premise of that is you trust this blob of data in the pod that's issued by someone, right, to be authentic.
Yeah,
right?
So here you do not trust these guys.
Right.
You only trust these original pods that were created here.
Right.
Yes.
Based on the public keys, right?
Or anything else. It could have been imported from an email, and it would be based on who sent the email. It could come, like, it doesn't matter. It's based on some way of representing an authority. Yeah.
So in the verification side, then, does it mean that it needs some sort of a trusted source registry that says that, you know, this identifier of this signer is trustworthy?
Correct, but it can be built on top. So you see how you have this pod here, right? So if you trust the system, what you trust is these statements have been done in a way that is sound from a logical perspective. Now, the way you would actually trust this pod is you have to check this number, right? Which is the public key of both of the pods. We constructed that logical statement. So the way I'm thinking about the system is I want to layer in trust on top of the logic. I don't want a big trust in the logic because I want to manipulate things that are linked to trust, just like I'm manipulating anything else. Mm-hmm. But you're right that for this to actually be useful, we would layer it and something else on top.
So eventually, it would need some sort of something like a CA certificate, like authority, that kind of
Yeah, and
architecture,
I think there could be many different competing ways even of doing that. Some people might use CA, some people might use a blockchain as a way to register schemas, but we don't want to bundle this with a specific kind of registry because we think it's a mistake that is being made by a bunch of projects out there where they're building this monolith of like the way we import data, as an example from Passport, the way we verify public key using this specific blockchain, the way we operate using these specific circuits. We want to unbundle everything, whether it's where the data come from, how the computation got done, and which registry of trust is being used. Yeah.
All right, thank you very much.
You're welcome. Cool. So how much time do I have?
5-10 minutes.
Dang. Okay. What would be more interesting? Making more pods, looking in the code base to show how a specific logical operation works. Something else? Beatboxing. Anyone has an opinion? Here. Code base? Cool. Let's look at the code base. I can't do two things at the same time. I'm a single-threaded processor. I would have to stop everything to beatbox. Okay, so cool. So this is a file that we have that lists all of the operations that currently exist in the system. It's just an enum in Rust. One specific entry here is greater from entries. So what this operation does is it takes two statements. You see S and S. What these statements need to be is they need to be value of statements. So statements that point to the value of an entry. And then if the entries behind these two value of statements, if the first one is bigger than the second one, it will add a new statement, which is something like greater than. We can check later. So let's see how that actually happens. So let's Command F for this. So, okay, I will not show you guys the front end. I will not show you how in the Lisp this gets turned into the specific command, but now you have to kind of like believe me that this command is called at some point pointing to the right statement. So first, one thing I'll show you is how to evaluate this statement in plain text, so not using cryptography. So if we see here, when I have the greater from entries, I destructure two value of statements and then the actual entries between them. And then I turn these entries into U64. And if the first one is indeed bigger than the second one, I create a new statement which is greater than the first key, the second key. So till then, this should make sense, right? Like, we're just showing how this happens in plain text. Okay, so now how does this happen in a circuit? So what we'll do here is first, in a circuit, every single one of these statements need to be turned into opcodes. And these opcodes are field element into the field we're using, which is the Goldilocks field. So the greater from entries gets turned into this opcode, opcode number 5. And then another thing I will do is it will take the operands of this statement, here it's S1 and S2, and turn them into a vector of operands that will be injected in the circuit as well. I think there's one last thing that this is just a way to sort these statements because they need to be sorted in a specific way. Okay, so in our circuit, here's what we do. So let's go to the top of our circuit. What the top of the circuit does, it says there's a current builder. The builder is just an object that you have in the proving system we use to be able to add new constraint. And there is a bunch of statements, right? And their targets. So this mumbo jumbo here is a way to be able to select from the list of entries we have the entry that corresponds to the statement. We need to do some like matrix kind of like indexing thing. So what we'll do here is we have this OP is valid array. So the code is still not great. Ahmad will tell you how we got there, but we'll make it better. But what you have to do here is you have to index. You can imagine, so the circuit model is not the computational model. You have to execute everything all the time. And then what you do is you have selectors that turned on for what you actually need to check. So what we do in this massive array, OP is valid, is we basically check the validity of every single operation that could happen on the statements that are currently being selected. And when you turn on the selector for the actual operation that we're doing, the other ones, we don't care about them. So the way this works is the selector for this array is going to be the opcode. So remember the opcode of greater from entries is opcode number 4. So 1, 0, 1, 2, 3, 4. Yeah, it's currently the fourth one. So when greater from entries is turned on, what actually gets checked is an end statement on whether statement, the first statement is indeed a value of statement, in the second statement is indeed a value of statement. So if you read this doesn't actually do the greater from entries, right? What it does is it just checks that you're doing the greater than on actual entries, not whether the first one is greater than the second one. So for reasons obscure that I discovered this morning, I will have to ask Ahmad why it's done this way. The place where we actually do this checked is here. So we have the greater than opcode target, and we say, hey, if the current opcode is indeed the greater than the greater from entries opcode, we do an assertion that says it asserts that something is less than, and here the statement 2 is less than the statement 1. So you'll see this is still a messy code base, but at the end of the day, everything, the operation that gets executed, at the end of the day just gets converted into some circuit operation. And so you also notice that it's actually pretty easy to add new operations, right? Like here, we just had to add like 8 or 9 lines of code to add an operation. Of course, there are difficulties when you start having complex data types like arrays, etc. But a lot of the difficulty in this system is to write everything else that happens on top of these logical opcodes so that you can manipulate them easily. Because one thing we did is we have this massive test that checks this kind of like web of trust like computation. And when you write these opcodes yourself, it just takes hours, and most of the time you get it wrong. So like a lot of the smart stuff here that makes this easy to use comes from the logical programming language, right? And then the layer on top. Of course, you have to write the circuits correctly. Some of the circuits here is like pretty tricky. Like if you want to show that an entry is contained in an array, you should do this using like a Merkle proof as an example to make this more efficient. So there's a lot of work here, both at the programming language, at the logic level, at the circuit level. So I'll stop here for questions or for future prompts. I think we have 5 more minutes before I pass it off. And we can also do maybe a light Q&A. Cool. Okay. Done here? Yeah, this is a good question. I think, so as I've been working on, so my role here was to work on the PEX language. And what I've discovered is like every time I want to make more complicated program, I have to make the programming language smarter, which is not a good sign. So that means we're probably doing it in a wrong way. So one inspiration we have, which is still a little bit out of touch with what we're trying to do, is interactive theorem provers, so like Coq, Iris, etc. But these are heavily human-assisted, and also they're like very complex beasts. So I would rather not have to write an interactive theorem prover in order to make this useful. So yeah, I've been trying to find in the literature outside people that have been writing programs in an imperative way or in something that's not like a theorem prover, in a way where you can turn that into logical operations. And there is some cool stuff out there. There's this programming language called Agda that you can use to make proofs about its own correctness. And it's like not that bad to use it. So yeah, there's still a lot of work to do there on like the right way to express this. One challenge that we have, that we set ourselves to be able to achieve with the language to then decide if it's the right way to do it or not, is to be able to construct pods that might recurse like an infinite amount of time. So imagine a kind of pod I would like to construct, which is a pod that shows me how far away I am from someone. So what this would mean is, let's say it's from how far away it is from Alex. So Alex issues a pod to all of his friends where he has a bunch of logical statements that says he attested to someone's public key. And then these people can attest to someone else, like me, because I don't actually know Alex directly. And then I would like the pod there to have a number that says I am 2 degrees away from Alex. And I want to be able to like do it for someone else and be 3 degrees for Alex. So there's a trivial way to do this where the size of the pods in terms of how many logical statements it has increases linearly with the distance from Alex. We would like to do this in a way where the number of statements does not increase linearly by having more powerful logic where we can count using probably first order logic or something else like that. And also where the script, the PEX script that we write for this is the same for every degree of separation, because currently the way you would do it with the current PEX, you would have to write different script for each degree of separation. So if we can do that in a way where it's constant size script and constant size logic, we would be pretty happy. If we cannot do that, then we'll have to revisit our approach. Cool, and I'll close it here. Now we're gonna have a talk. So everybody wake up, different person, different style. We're gonna have a talk from Arno and Ahmad about the circuits and how they were put together. So here I showed you guys the easy part, which was putting the operations together. The really hard part of this was making this system like basically infinitely recursive, where you can ingest multiple pods, some Schnorr pods, some Plonky pods in a way where you can keep recursing, and that was pretty tricky to do correctly. So that will be the next speakers. Do you guys want to come on stage? Thank you. And while we prepare, if anyone has more questions, I can answer them. I'll just take the mic.
Hey, yes, hey. So some guy talk about K and the matching logic over there.
Yeah.
So how hard would be to plug the result of the K execution, so the magic logic over there, into pods?
Yeah, I think so. We spent a bunch of time looking at K, even writing some like little K definitions ourselves for like toy languages. I think the way we're thinking about this is we really want to figure out like what's the right tool for the job, you know, because we were thinking about like, oh, should we just like write a ZK proof for like the Coq theorem prover or something like that. And there's been a bunch of work there from like students of Dan Bonnet as an example, but these proofs are incredibly expensive and really hard to put together. I don't know what are the numbers yet for something like K. I don't know if you guys are writing proofs yourself or using something like a ZKVM, but it's probably very expensive. Like the pods we put together here, they take like 2 seconds on a laptop, so that's pretty neat. But in some ways, what I would like is one thing that would be really cool is to be able to dynamically size the complexity of the logic based on the claims you're trying to make and use less powerful kinds of logic that are faster to prove or more powerful kinds of logic that are more expensive to prove. That would be a really cool system. Where as an example, you could tap into K if you want to make like really complex proofs and very powerful proofs. But if you just want to show you ages over 18, you can just like make that pod yourself in like 30 milliseconds on a phone or something like that. But yeah, I would be interested to look more into it. Are you working at Pi2?
Awesome. Yes.
Okay, cool. Yeah, so you're the guys that like prove the K framework execution, right? Yeah, we can chat about this.
All right. Thank you.
All right. Welcome to our lightning talk on Pod 2. Show of hands. Who here is not yet sure what a pod is? Who here is too afraid to put their hand up? Okay, at least one person. So pods in a nutshell, you basically have a key value store of some sort. You cryptographically, sign it in some manner. I'll say a little bit about that in a moment. We'll be talking about the next generation of pod that was already alluded to by Justin. And a summary of Pod 2 is that it allows for easier composability than Pod 1. That's essentially it. All the advantages of Pod 1 are there in Pod 2. It's just a matter of being able to compose pods, which we cannot do with Pod 1 in quite the same way. So just a QR code with a link to our repo. You can find all the code here. Justin's already provided this link, but here it is in the form of a QR code if you like to scan QR codes instead. So we actually have an ongoing port of Pod 1 to Rust, and that's in the ParkNet pod subdirectory. And then Pod 2 has our current efforts in developing Pod 2. So Pod 1, so far, as I mentioned, you basically have a key value store. You Merkleize it. This isn't an entirely new idea, but it is a solid one. There's a nice blog post by Joel Gustafsson, Merkleizing the key value store for fun and profit, worth reading. And we construct things in such a way that it's easy to make ZK proofs about these things, yeah? So we use the appropriate signature scheme and so on, so we can use Groth 16 for our proofs. And the ZK workflow for Pod 1 is essentially you take your pods, you have some kind of configuration, proof configuration that says what you want to prove, and you plug that into some procedure called GPC prove. What you get out of that is a Groth 16 proof together with some revealed claims. And this is the rough workflow. Now, let's say you wanted to take the output of this and generate a brand new proof. So something like, taking a bunch of pods, taking a bunch of proofs, revealed claims, putting it in a box, and then spitting out a brand new proof. But how do we do this? It's not entirely clear how to do this with our current setup using CIRCOM and Groth 16. Now, why would we not proceed with Groth16. Why is Groth16 not suitable for this application? Arnau?
So very quickly, the main idea here is like we can do recursion over the Groth16. It's just like it's too expensive for like most of like the real world applications. The main idea is that this brute force recursion will be like we define a circuit that verifies like a full proof of the same system. So in Groth16 will be like having a R1CS circuit that verifies like the logic of the like pairing checks and so on of a Groth16 proof, which requires some like in the worst case like some non-native arithmetic of the elliptic curve, which is very expensive in circuit, and in some cases where we can use some curve cycles, we can get this a bit down, but nowadays we have like some like more efficient options, such as like the Stark side of things. We're using also some of those like small prime field systems like Goldilocks in the case of Plonky 2 or Marcin primes in Plonky 3. We can achieve this like kind of recursion, which like instead of taking like millions of constraints, it takes like hundreds of gates, and then it's like it translates as like smaller proving times, like a few seconds.
So, so far, as I mentioned, a pod, well, actually I didn't exactly mention it, but essentially a pod consists of a claim and a proof. Here, yeah.
Sadly, we did not sync up on this one. So one thing I'll say is this is pod 1, which is a system that's currently used for frogs, etc., which has limitations. And so Ahmad and Arne are going to talk both about pod 1 and pod 2. What I showed you guys is pod 2, just so it's super clear. Sorry for that interruption.
Exactly, no worries. So essentially, we have a claim and a proof. With pod 1, you essentially claim I have this key value store, some party with this given public key attests to the validity of this collection of keys and values, key value pairs. And then the proof is just a signature. But then when we plug it into that box to get a ZK proof, we get something of a completely different form. Our claim is that we have a proof config, and it is consistent with some set of revealed claims, like maybe you reveal your date of birth or something out from an ID pod. And then the proof would just be some Groth16 proof, like plus or minus some extra bits to say exactly what circuit we're dealing with, like, you know, artifacts. And so you can see it's sort of heterogeneous here as far as the form of claim or proof. And our approach now is to kind of unify these in such a way that the claims should be of roughly the same data type. And that's where pod 2 comes in. And in a nutshell, we, again, have a claim and a proof. The claim is basically we have a bunch of statements, named statements. So we have a map taking some key. You can just assume it's some identifier. It doesn't really matter what form it is, to a statement. And our proof is either going to be a signature of some sort, kind of like with pod 1. In our case, we use a Schnorr-type signature scheme, but we're kind of branching out from that. Or it could be a ZK proof in the form of a Plonky 2 proof. So we've shifted from Groth16 to Plonky 2. And now, what is a statement? Well, to get into what a statement is, I need to tell you exactly how things are laid out. But let's just start with statements. A statement could either say nothing at all, or as Justin said, you could say, hey, the statement is, I have a value, this is its name, it comes from this place. And in this case, we have a notion of origin and anchored key. I won't really say too much about that, but the rough idea is we're going to have processes for constructing new pods, and we kind of want to say how these new pods were constructed in the process and keep track of their origins. Yeah, I mean, we have other such statements like equality, non-equality. Inequalities are also in there, but I just omitted them here. But then we have things like sum of, which Justin already talked about. And to actually construct statements, you apply operations. So again, we have like no-ops, constructing new entries, copying statements, and so on. And the idea is we're going to have these boxes where you can actually take pods, and all you could do, you could just copy statements from these pods and verify that the copying was done properly in ZK. Now, as I said earlier, we kind of had, we had pod and GPC. They're kind of like two completely different animals. Here we have a pod, and we have pods of different types. Now, claims will always be maps from keys to statements, but proofs could differ in their formats. So we define a Schnorr pod to be a pod whose claims are of the form a value of key is value. Yeah, so all of its statements will have that form, and the proof will always be a Schnorr signature. Now we have the notion of an oracle pod, which can take claims of any form. So here we're assuming there's some trusted party or some trusted machine in the cloud. Perhaps we have a fully homomorphically encrypted setup going on, where we could just pass all this data to some server, and it's going to run those non-ZK programs, and it's going to take a bunch of pods, and it's going to check that this entry in that pod is greater than that entry in that pod, and then it's going to spit out a brand new pod attesting to all of that. So we call that an oracle pod, and it is pretty much a Schnorr pod with a God-given oracle signature, basically. And well, why would we have this? Well, besides being optimistic about fully homomorphic encryption, and perhaps even multi-party computation, it gives us a model of what the ZK circuit is going to do just outside of ZK. And that's what a Plonky pod is. It's basically an oracle pod, but done in the circuit, and the proof is not a signature, but a Plonky 2 proof. And I mean, as I said, you basically want to take some data and construct a pod out of it. Some data, yep, 1 minute? No? 2 minutes? Okay, great. We have gadgets. Constructing pods, you use gadgets. That's our terminology. That's essentially what the slide says. So you can construct a Schnorr pod using a Schnorr gadget, which basically means taking this key value store, the secret key, and bam, Schnorr pod. And similar deal with Plonky gadget. I'll sort of rush over to the ZK circuit because we don't really have much time. But long story short, we have a recursive circuit in Plonky 2 where we plug in a bunch of Schnorr or Oracle pods together with Plonky pods. We verify signatures or Plonky pod proofs, Plonky proofs. And then in the circuit, we check a bunch of stuff. So we also have to keep track of where these pods come from, where their values come from, and so on. All this stuff has to be checked in the circuit. The operations have to be applied, yada, yada, yada. Plonky pod comes out. Future directions. The workflow needs to be streamlined. The cryptography is not that strong at the moment. We kind of want non-native arithmetic, non-native schemes. So we want to use our pod 1s, so BN254-based crypto in this 64-bit field, which is a bit difficult. And that is essentially what leads to the backwards compatibility that we're kind of hoping to get out of this. Yeah. By the way, these slides are on my GitHub. I can link to them if anybody wants to have a look at them later on, so you don't have to take pictures. Thank you very much for your attention.
For a bit. We have a little bit of time for questions for Arno and Ahmad. So, oh yeah, we have a hands raised there. Arturo, do you have a mic?
So, do you think of roughly the Schnorr pod as like a self-attestation? The Oracle pod as anything that you would use via an introduction gadget will come in as an Oracle pod, whether it's originally like a proof from a ZKVM or something signed or whatever. Is that just how things will sort of always be introduced? And then the Plonky pod's always within the system?
Kind of, sort of. Actually, I would view it slightly differently. The introduction gadget, at least the way I viewed it, was more to go from our legacy pod 1s to Schnorr pods, actually. So Schnorr pods are pretty much exactly the same as the pods, the frog pods, the ticket pods, etc., that we've had so far. What's that? No, they wouldn't be Schnorr pods, but they could be. They could have been Schnorr pods. It's just that we had a different cryptographic scheme. But if you take those, you would use the introduction gadget to get a Schnorr pod to then use here.
But you wouldn't get a Schnorr pod because it wouldn't be Schnorr signed. It would be a ZK proof on it.
Yeah. Well, I'm saying, okay, so you would essentially get a Schnorr pod, but you do that in ZK so that you don't have to actually attest.
Well, I guess we could call them differently. Yeah. So there are many ways to do it, I guess. I think the comment you made, which you're right about, which is like things inside the system would be Plonky pods. It's true that Schnorr pods are going to be basically self-attestations. And then foreign cryptographic data being imported, one way we could do it, which is not necessarily the right way, I mean, the way Ahmad described it works as well, is we would make a new gadget type for each new kinds of data that you would import, basically. So you would have like an email pod, if we were to import stuff from a user's ZK email, we would have a passport pod for like a specific kinds of passports.
Okay, that's what I was sort of wondering, is if you were going to try to import them under the same pod type or just introduce a new specific pod type for each one.
And so the cost of having a new pod type is you need the verifier for that pod type to be part of the spine pod, right, the Plonky pod. So one tricky thing is if ideally you would get to a stage where you don't need to embed the verification key for all of these gadgets into the spine pod, and you would be able to like dynamically load them by witnessing them and having like some form of like certificate authority system or something like that, but very much work in progress.
Thank you.
I mean, I think we do kind of need a new type. It would essentially look like a Schnorr pod, but with the ZK proof instead. So we'd put some constraints on the types of statements you'd have in there.
It seems like we're super out of time. So our next speaker is Ayush Gupta. Ayush Gupta is going to talk about ZK email. So ZK email is a way to introduce cryptographic data from email systems. And it's very much philosophically fits within what we've been talking about over the last hour, which is making use of cryptographic data and computing on top of it.
Cool. Maybe just so I can get a sense of where people are at and how much I should spend on background, maybe like raise your hand if you've heard of ZK email or seen any of our talks this week. Okay, cool. So in that case, I'll kind of skim over the basics and I'll focus more on the like interesting new stuff that I didn't cover in all of our other talks. So we'll quickly go through the basics and I'll talk about some of the interesting infrastructure that is relevant, not just for email proofs, but generally for provenant data proofs, and one vision of how doing this sort of programmable cryptography might look like, and then hopefully expanding the sense of what you can do with like weird applications that are kind of half ZK email and half other primitives that might lend itself well to the idea of, oh, like what if you like compose these proofs, can you get more interesting things? Okay, so the first thing I want to talk about is how I see adoption of, say, cryptographic technology in the context of all the other cryptographic technology. If we look at cryptographic infra over the last 10 to 20 years, we see that there is a practice of making things more user intuitive, but not a practice of, say, like private key ownership. So for instance, with VPNs, it was very hard to set them up at first, and then now it's much more turnkey, and that adoption curve maybe took like 10, 15 years. End-to-end encrypted chat. Initially, you had to roll your own PGP. Now you can use end-to-end encrypted messengers. Previously, you had to roll your own Tor. You had to find your own exit nodes. Now you can just use Brave incognito mode. To have TLS, interpret TLS, or have TLS on your website, you had to do very bespoke certificate stuff. Now it's all happening by default. And similarly, you can make a similar argument for, say, like blockchains or Web3 data, or even cryptography in general. And one of the main takeaways here is that like there should be an easy way to do these kinds of proofs where you don't have to punt private data to a server. Because in all the technology we've seen in the past, where cryptographic technology is like the purpose of the thing or the end game, like you never want to manage private data for users. It's always on the client side. And I think folks alluded to this in many of the earlier talks, but there's lots of digital signatures you can take. You can take passkeys, you can use this to do transactions very easily. You can take passports, you can use this to prove citizenship. You can take Apptest, you can use this to prove execution of some app on your phone. And of course, emails. And the really interesting thing here is that as long as you have a digital signature, you can put a ZK proof on top of that and then verify that off-chain data on-chain. And so the hope is that seeing more of these and driving more of this adoption can make this kind of concept of cryptographic interoperability more tangible. And so I guess most folks already know this, but emails are signed according to the Deacon protocol. We stuff this into a ZK proof, and we add selective privacy on top. This means we can keep whatever data we want in the email private. We can directly verify the Web2 mail server, and we can verify them on-chain. There's a bunch of interesting primitives that we're thinking about. The nice thing here is that we've tried to abstract these all the way, so we have libraries for all of these things in all of the different ZK proving languages, and we're constantly iterating on these. But the hope is that users actually creating these kinds of proofs should not have to think about the details of which of these primitives they're using. And one simple idea of something you could do is very simple email redaction or whistleblowing, where you take an email, you highlight what you want to hide, and you reveal everything else. But you can do much more complicated things. One cool thing that ZKP2P recently built is a domain marketplace on top of Ethereum where you can prove you transferred a domain on Namecheap, you get a confirmation email, and you use that for the seller to unlock the escrowed money that the buyer locked on-chain. And this is quite interesting because this means that you can, as long as you have a signature, you can build markets on top of it, you can build interoperability on top of it. But how do we have 1 million ZKP2Ps? And so the idea is you need to be able to make these new kinds of proofs very, very fast and integrate them very, very fast. And part of this is the pod's vision. It's very easy to select which proofs you want. And part of it is actually defining these kinds of proofs in a very bespoke way for each proof system. And so one of the visions we have is that it should be very easy for an app developer to not have to think about these details of what is the backend of the cryptographic infrastructure they're using. They just say, I want it to happen on the client side or on the server side, and it should just happen. And so we've investigated all of these. We've created primitives in many of these languages. But the point is that we decided to abstract this away so that you kind of had the proof system decided for you. And so the idea is you can say, look, I want this specific ZK email proof, maybe the proof that you got, say, rejected from DevCon, and then I'm going to specify whether I'm local or not. And I can put other parameters here if I want to be more selective, like, oh, I want this to be, I want the pod version of this, I want it to be composable with Rust, whatever it is. And create prover will automatically determine the best prover for your use case. And then when you actually want to use it, you can just call exactly what you want to do, generate proof, verify on chain, whatever, and it'll just happen in the background for you. And the hope is that, again, by abstracting this away from actual developers, you don't have to think about the ZK as deeply anymore. But how do you actually create these proofs, like that DevCon rejection proof? The hope is that you can make this really easy to make. So we've done a bunch of iteration with folks building different kinds of patterns. And we've kind of settled on this flow that seems to be intuitive for most people, which is basically you name your pattern, you upload an example email, and then we autofill a bunch of information from your example email. So we say, who is the sender, what is the selector, what are all the different lengths, and we will autofill this information for you. And then one of the things we notice is that when you actually want to parse the email, you have to basically define this like regex to do that. There's a great Goran post where he talks about how regex is kind of like a very early vision of neural networks. It was like the folks who were inventing this stuff were like, oh, like regexes are really powerful. And so that's part of the reason that we rely on them for a lot of the parsing. And in a kind of a different way, we basically we notice one of the problems is that people often don't define deterministic regexes very well. Many folks, because there's some constraints like, oh, you can't use lookarounds, you can't go back, or else you break some of the, things become a lot more expensive. We basically train this AI on all of our patterns, and now the idea is that it'll automatically, you say, oh, I want to extract the username out of this body, and it should automatically generate something that'll extract the username out of that body. And so the hope is the flow of making these proofs is much more intuitive. And you get kind of a pattern that looks like this. It's maybe 20, 25 lines. You don't have to read it, obviously, but it's basically some regexes of where you're actually parsing, the domains and the parameters of the email itself, and this will just get applied to all the relevant emails. And then the cool thing is, imagine you want to reuse some proof that somebody else is using. You see, oh, I want to reuse Namecheap's domain proof, and instead of building a marketplace on top of that, I want to unlock another domain the other way or something. You want to build some other composable thing on top of it. Then you want the ability to look at existing proofs that everybody is using, making on chain, verify them, reuse them. And so we have this nice little registry where people can look at all the existing proofs. And the really cool thing is there's sort of this Vercel-like vision where you want to be able to deploy things very easily. So once you've defined this pattern, we automatically deploy this little front end for you where we say, look, we're automatically going to create this thing where you can sign in with your Google account. We'll filter which emails should be in fact parsed. So if you look at the bottom, we filter their inbox to say, these are the correct emails that will parse for this kind of proof, and the user can automatically verify them. And so, another interesting analogy that I think we see in normal development space that we haven't yet seen in the ZK space is how do you actually do this kind of version history? Because these emails change formats all the time, or people want to maybe fork the pattern for DevCon rejection to ship DevCon acceptance or something. And so you want a very natively integrated GitHub-like capability to say, oh, I like this pattern, but I want to tweak it a bit, or I want to use an older version for this older email or whatever. And so building these kinds of version primitives, I think, is very powerful. Folks have built a lot of cool stuff. Someone built a Dropbox verification. Someone built proof of flight ticket from one, and you only reveal from and to. Someone built you're part of a Slack workspace. Now you can start to see how this composability really matters. I can prove now that I'm part of the company Slack workspace, and I took a flight to Bangkok, and now I'm going to get automatically reimbursed on chain. And so as you start composing these together, you get very interesting, powerful primitives. You can prove you exported your LinkedIn data, and then you sell that to OpenAI. You can prove you exported your OpenAI data and then sell that to Anthropic. You can prove you completed some issue on GitHub and automatically get paid. You can prove you ordered pad thai in Thailand. You basically have a grab receipt that shows your location is Thailand and pad thai was in the order. And of course, that you maybe got rejected or accepted to DevCon. And now you can see how this SDK makes a lot more sense. You just choose the one you want to import, and then we can automatically fetch that from the registry. Yeah, so this is live. Folks can try it out. Another, I think, underrated piece of infrastructure is archiving these public keys. This is the case for DKIM, but it's also going to be the case for all the other public keys on the internet. The country public keys for passports, the ID public keys for ID cards. There's not really a clear archive of these keys anywhere. And so our hope was that we should make it easy for folks to see these old public keys and then access them where they want to. And why is this relevant? So here's one example. This is Hillary Clinton's email inbox. From 2016, we ran DKIM verification over all of it, and these red ones are the ones that no longer verify because we no longer have those DKIM keys. And this problem is going to happen more and more. Like as we build these signature verification primitives, we need a place where we can settle these public keys. And for DKIM, it's very easy. You just hit this DNS registry, and you can kind of search on this archive. And the hope is that, right now this is one server that's doing this archiving, but you could imagine you can build a whole consensus layer on top of this. You could have a bunch of own independent archiving nodes, and when you want to fetch a value, you say do a threshold signature over all those archiving nodes, and you say, look, yep, like 10 out of 10 of the archiving nodes said that this was in fact the public key on that day. Sounds good to me, and you can kind of almost build a consensus network that is just archiving keys. And there's one cool trick specifically with RSA where you can recover lost public keys. So we were able to like get public keys from 10 years ago that no longer exist, and you do this like cool RSA GCD trick that I don't have time to get into, but you can look at this if you want. It's pretty nifty. And then users have to contribute how they actually like access these keys. So for emails, you have to contribute the URL. For passports, you'd have to contribute the country kind of URL. And so it has to be some kind of mechanism to contribute to this kind of archive network. Cool. And then maybe to inspire a little more, I'll just kind of rapid fire some applications. One thing folks have really wanted is the ability to use Google sign-in directly. So we kind of built this cool primitive where you can enter a command and then sign in with Google, and the sign-in with Google will sign that command and then prove it on chain. You can do kind of credible whistleblowing or domain proof. So for instance, you can prove you work at a company. And then the question is, how do you do moderation on anonymous message boards? So for instance, maybe you want to prove you worked at Boeing, but you don't want to reveal who you are, but you want to say, look, I forgot to put screws on that plane, maybe don't fly in that one. Well, the best way to do this is you prove you're an employee there, and then we do moderation with TEEs with this kind of teleport style thing, which is quite cool. You can have email triggered transactions. It kind of looks like you'll get an email like this, or you'll do a sign in, and you can approve a transaction on chain. It's very easy to build this kind of thing, and yeah, I'm excited to jam more, and I'll take any questions.
Any question? Okay, I have questions.
Yeah.
So you were talking about the idea of having kind of like a consensus network to save public key. From your perspective, like what's the actual, like what do you think personally is the scalable way to just like Google search style, just like save the whole internet, like public key, from a public key perspective? Whether it's like HTTPS certificates, domain name public keys, etc., just everything is being used.
Yeah, it would be really nice if you had signatures. So like if these countries added SXG or RFC 9421 to their web pages, you would have direct signatures that then you could save, and you don't need a network anymore. You need one person to save the signature, and that's good enough. Unfortunately, like many of these keys are distributed across various internet infrastructure, like certificate authorities that aren't really on the internet or on a website, or on like DNS without DNSSEC, they don't have signatures. And so the classic method of like, yeah, ideally we could use a Wayback Machine to do this archiving, but much of this stuff is not on like a HTTPS web page. It's on some other public key infrastructure that's not directly tied to the internet in some easy way. And so that's why I think we want this like other paradigm of archiving. But yeah, I wish Wayback Machine just added the ability to do this. Yeah. Yeah, it's a good question. Like we are like, how do we think about the risk of bootstrapping this on top of the DKIM standard, which may not have been engineered to do like all the security things we want it to do? And maybe one thing I would say is that this is sort of like an intermediate transition. Like it's kind of, if we want to get signed data everywhere, and if we want to get really like all those private keys to be in like super secure TEEs or whatever, down the line, we have to prove to people, hey, you can do interesting stuff today. And I think that a lot of that comes from like, look, like you can do these interesting composable proofs. Oh, you can do account recovery. And like, yeah, the security is like the same security as the ability for you to send from another Gmail account. Like, you know, if you can do that, you can break the system. But the hope is that like Gmail, Outlook, et cetera, have engineered their systems to be good enough that this works at a small enough scale. And then hopefully you can eventually get proof there's more robust signatures. People add DNSSEC because they realize, oh, this is a real thing people want and are using. So I would even say this is like a transition period of how, oh, we need to connect these kind of worlds of data before all the data is signed and verifiable.
Hello. So here I'm going to talk about cyberfrogs. If you've played around with the frog game by registration, you might have seen one of these things. This is a little box, a little sort of custom circuit board, a PCD, PCB, if you will, that it has the ability to generate pod v1s entirely on a kind of pod pipeline that's built using to run on this very small, cheap, RISC-V processor. So first, and I think that there's a couple of lessons here that I think are going to be interesting to people interested in sort of general software programmable cryptography that I think parallels hardware. I think parallels programmable cryptography in particular ways. So going back to some history stuff. This is ENIAC. Oh, it's, wait, okay. This is ENIAC. It's from 1945, one of the first computers. It was $7.5 million, and it ran at 0.05 megahertz. A few years later, there was the Apollo guidance computer, $4.4 million, 2 megahertz. And in 1984, we had the Macintosh, about $7,000, 8 megahertz. This is Moore's law, roughly. So this is the CyberFrog. It costs about $5, totally custom, ordered and designed and fabricated, and with essentially this cost over the course of about a week. It runs at 160 megahertz. So you can see, and it has a RISC-V core, and that specific core is about $1.60. And that sort of shows the scale of how Moore's law has essentially made computers super cheap, super small. And I think this is kind of a diagram, I think, that shows some of the parallels between, in the past we had these big room-sized supercomputers that sort of do the equivalent of sort of the very small amount of compute that you can get for literal pennies now. And if you sort of go horizontally and preserve the scale, the size and cost, you end up with essentially the latest AI supercomputers. On the right is the latest NVIDIA DGX super cluster thing, which is sort of the equivalent of a few trillion hertz versus 5,000 hertz. On the bottom, you can sort of have, you can see this arrow. It's kind of meant to represent essentially conservation of sort of compute quantity. So this $1 processor has actually orders of magnitude more compute capability than that original ENIAC. But you can also end up creating an even slower computer on top of that trillion terascale supercomputer, and that's sort of the overhead of a lot of these programmable cryptography systems. If you've played the Frog Zone thing, also, that's sort of an example of the sort of tremendous overhead that some of these frontier techniques involve. So going back to the cyberfrogs, I think there's another aspect besides the sort of computational capability. Oh, and I think what's sort of interesting is basically working with this sort of very cheap, dollar scale infrastructure. You're sort of playing with a restricted computing environment the way that you sort of are when you're working with sort of programmable cryptography environments. You're they're both sort of situations where you're sort of artificially working with relatively cheap or relatively slow computers. So I think that's the first half of the first parallel, I think, of why sort of playing with hardware is interesting. The second one is that they're both called circuits. When you're working with ZK snarks and also when you're working with electronic circuits, they're both naturally circuits. On the left, I have this is a screenshot from ZK-REPL, which is a little CIRCOM developer environment that runs in the browser that I built a few years ago. And on the right is a screenshot from EasyEDA, which is also a web-based, very easy to get started with a system for designing circuit boards, including the CyberFrog, which this is a sort of screenshot of part of it. You can see that they're both about sort of declaring signals. One is a graphical interface, the other one's sort of more code-like, but ultimately it gets compiled down into something that in the electrical world is called a netlist. It's pretty much equivalent to the sort of R1 CS sort of representation that is sort of the intermediate part of CIRCOM that eventually turns into like sort of Planck or Groth 16 or whatever. So you have this, and then at the end, it gets compiled into a sort of like physical representation, by some sort of compiler. On the left is sort of a little application that generates, that takes that sort of R1CS stuff, turns it into like a little Planck prover, and then on the right you have the sort of laid out PCB for the frog. This is sort of the tail section. And so, like, I think basically there's two things that I think are interesting. Like, one is sort of working in these constrained environments are kind of similar and kind of fun. And the second is sort of structurally, when you're working with hardware, you're building circuits, and a lot of these circuits are develop a lot of similar mental models around abstraction and connecting things together that also apply. And actually, it's just like, nowadays with how cheap it is to manufacture stuff in China, like, I think if you have the skills to like build circuits with like software and like ZK Snarks, you can also pretty much apply a lot of those same skills to building sort of physical things that are shaped like frogs. So yeah. Happy to answer any questions.